Cool. So this is the 2018 Electricity Level 1 exam. Um, so for question 1, they tell us to draw positive charges across a non-round metal object. So where the object is not as round, so around here all the way to here, charges are supposed to be drawn very close to each other, and where it starts getting round like this, you can space the charges out. It's a pretty straightforward question. You probably learned this stuff in class. So on to the next one. For 1b, we explain why copper is a better conductor than glass, and so copper is good because it has free electrons. So it has free electrons that are free to move around, and they can go around easily. So copper is good because it can facilitate the flow of electrons, and the flow of electrons is basically current, and therefore this is a good conductor for electricity because current is electricity, and therefore glass is bad. And glass is bad because it has no free moving electrons. And therefore, if there's no flow of current, no flow of electrons, and if there's no flow of electrons, there is no current, so it's bad for electricity. In fact, glass is actually a insulator. It is not even a conductor. On to question 1c. So for 1c, they give you the generator can generate 2 megavolts, which is 2 times 10 to the power of 6. Remember, we always use this because this is an SI unit. The spark lasts for 0.01 seconds. This is the time, and it literally says 100 kilojoules of energy. So this is the energy. The question tells us to find the amount of current. So okay, so we have the voltage, we have time, we have E, which is energy, and we need to find current. So the first equation we choose from the formula sheet is P equals E over time, and this will give us the answer for power. So 100,000, this is basically that, 10 to the power of 5 joules over 0.001 seconds gives us 1 followed by 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. No, give us. So 1, 2, 3, 4, 5, 6, 7, 8. And that is watts because the unit for power is watts. And once we have the power, you can find another equation from your formula sheets. We can either use P equals IV or use V equals IR. Now we don't have the resistance, so straightforward, we cannot use that equation. And P equals IR will rearrange to give us looking for I, so I equals P over V, and the power we got is followed by 8 zeros, so times 10 to the power of 8 over the voltage, which is 2 times 10 to the power of 6, and that should give us the current. Putting that all into your calculator, should give you 50 amps. And that is the answer. Cool. So the next one is that current. So any current above 100 milliamps is extremely hazardous for humans. Okay. Explain whether or not the current created by this demonstration is safe. So the straightforward thing to do is convert both these numbers into the same unit. So we use the SI unit, which is amps. So therefore, to convert 100 milliamps into amps, we basically do 100 times 10 to the power of -3. Basically, we divide it by 1,000, which gives us 0.1 amp, and therefore 0.1 is, so the 50 amps we got is much higher than the 0.1 amps. So it is not safe for humans or anything really. Cool. The next question, you can have a quick read. Basically, it tells us to explain why the balls initially move towards the top disk, and explain why the balls then fall back. So as you can see, this generator is positively charged. And the main thing you need to remember is that, like charges repel, therefore, when you place something here, when you place anything here, due to gravity, it will flow down. And once it flows down, the balls lose electrons because this is positively charged. And therefore, if they lose electrons, the balls also become positively charged. And because like charges repel, the balls go upwards. And once the balls go up to here, they gain electrons because this thing is no longer positively, this thing is not positively charged, it has no charge. Therefore, the balls become neutral, and once they are neutral, the first thing neutral balls do is just flow down because that's gravity. They have no charge, they flow down, and once they flow down, the process starts again. They become, they lose electrons, become positively charged, go back up, lose electrons, become neutral, go back down. Like charges repel, positive charge, positive repel, pushes them top, and it basically repeats forever in theory. Cool. So this, you can have a quick read, but what it tells us is that the outlet provides 240 volts into 4 identical light switching power, and that is the power. Cool. So describe why the power strip must be wide and parallel. So the main thing you need to know is that voltage in parallel is the same. So if I wire this up, let me use white. If I wire this up, and here is the battery, so positive, negative. That's 1, 2, 3, and 4. The amount of voltage received by all these would be exactly the same, which is 240 volts. So therefore, voltage is the same, and in series it's shared, but we don't need to know that. For this question, you probably should know that though. So the main thing is that all the plugs, these are the plugs I'm talking about. All these plugs get the same 240 volts. Therefore, if one plug malfunctions, so basically if, say, the second one breaks down, even the third one and the fourth one and the first one will still have the same um, volts, the same voltage to function, so it'll still be usable. Um, Others can still. And this is really important because, say, if you connect something here and it blows out, make that clear. If you connect something to this one and it blows it out, in the series circuit, the current, the volts will flow here, here, and they cancel out. That's it. The circuit is broken. But in a parallel circuit, if this blows down, the current flows here, then here, nothing goes there, but still goes here. So all these will still function, even though this one does not function. Cool. So question 2b. Connects four identical 60 volts lights in a parallel with a 240 volt DC supply. Cool. So we just showed that the current equals 0.25 amps. So from this we know that the power equals 60 watts. The voltage, and here equals 240 volts. And we need to show that the current equals 0.25 amps. So looking at the formula sheet, the only possible equation you can use is P equals IV. You can rearrange that to I equals P over V. Plug the numbers in, 60 for power, 244 volts, and then I should equal 0.25 amps, and that is proved. Sweet. So bulb C is replaced by energy efficient light, a lower power rating. Cool, so lower power rating. But it has the same brightness. Okay. Explain whether the energy efficient bulb has a higher or lower resistance than the original bulb. So if the power, as the power rating is low, if the power is lower, and we know that because of the same brightness, the voltage stays same because it says it's the same brightness. Voltage stays the same. Therefore, according to P equals I over V, we know that the current has lowered according to this equation. If P goes down, I stays the same. In order for the equation, the P equals I over V to stay balanced, to stay the same, I must go down because the answer, the value for P has gone down. So if I goes down and V stays the same, according to R equals V over I, the R must be higher. That's according to this equation. Cool. And that's pretty much all for that equation. So the main thing for this question is to look at your equations and say if one number goes down. So for example, if I goes down and P stays the same, therefore something must happen to this number, or vice versa. You know, if say if I goes up, V stays the same, therefore something must happen to this number for the equation to still be the same. Sweet. So D. Anything? No. Okay. Well, that's just extra space. Okay. So D. Andrew tries to replace all four bars in the center. So the total. I haven't read through the question, by the way. So the total current is this. Electrical energy used by 1. We need the electrical energy this time. Okay. Period of 2 hours. So the first thing to do is make sure all the numbers you're using are in SI units. So SI units. So yep, that's amps, energy. We need to find energy. 2 hours. So for time, the SI unit for time is seconds. Therefore, 60 times 120 minutes will give us seconds. So from this, from the data provided, we know that I equals 0.2 amps. We also know that times, so 60 times 120 plugged into your calculator should give you 7,200 seconds. We need to find, oh, yep, there you go. Oh, no, sorry. So we need to find P for the first bulb and the E for the first bulb. From here, we also know that the voltage is 240 volts. So looking at your formula sheet, the first equation that comes to mind is P equals IV. Therefore, for power, we need to get 0.2 amps, 0.2 times 240 equals 48 watts. That is power for the energy efficient bulb. After that, the second equation that comes to mind is the P equals ET, because it has pretty much everything we need. It has the E we're trying to find, it has P which we have, it has T which we have. Therefore, rearranging for E, which is the energy, gives us E equals P times T. Therefore, 48 watts times the 7,200 seconds. Plugging that into your calculator gives us 345,600 joules of energy. And that is also for the energy efficient bulb. Cool. And for the AND part, compare this with the energy used by 160 volt light bulb over 2 hours, and that's the original bulb we're talking about. So for the 60 watt original bulb, so we can use the same equation, PT equals E. Therefore, 60 times the same 2 hours, which is 7,200 seconds, gives us, plugging into your calculator, gives us 432,000 joules of energy. And that's for the original bulb. So from this we can see that it tells us to compare the results. So at the bottom of the equations, just write that the original 60 watts bulb uses more energy than the energy efficient bulbs. Okay, cool. Sweet. So on the diagram above, label the magnetic south pole, and that's what it is. Cool. So you could use a number of different rules, which says here, state the name of the rule. You could use the right hand rule. Um, what else? You could use the rule that current flows north to south, which is the one I'll use. But you should probably stick with the right hand rule, to be honest. So if that is plus, we'll go this way, so that'll be north, and obviously that'll be south. We'll just write that in a better way. So the way I figured that out was because the battery is here, that's positive, 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 positive to negative, which will be north to south. But you should stick with the right hand rule method. I think they teach you that in class. So now closing the ignition switch. Ignition switch is here. So cool. So when this switch here is closed, we can say that the current starts to flow through the circuit, and as the current flows through the circuit, um, the what's the name of the solenoid becomes so the solenoid becomes magnetic. So as the current flows, whenever current flows, a magnetic field is produced, is created, and that's the rule. So when the current flows, there will be a magnetic field produced in this solenoid, and therefore this will become magnetized. And as it becomes magnetized, we know that magnets attract the iron. Therefore, the magnetic solenoid, due to the flow of current, will attract the iron switch. Furthermore, and therefore it will close that circuit, making this a complete circuit, basically. So we can write the current starts to flow, the solenoid become so the current starts to flow. A magnetic field is created / produced. The solenoid becomes magnetized, attracting the iron. Therefore, this closes the circuit and completes it. Cool, so next question. Draw the direction of the reference. False. Cool. So there's an arrow going this way, and I'm pretty sure you can use the right hand rule for this, but if the current flows that way, current flows from north to south, therefore current will flow this way. And from this, you can state that these are going in, and it will be coming out here. Cool. That's just using the current flows from north to south, figuring out that this will be the flow, and therefore it'll go inside here and then come out here. Remember, this is for going inside, and this is for coming out. Cool. So produce. So 40 Teslas at a distance of. Cool. So 4 times 10 to the power negative 5 Tesla at a distance of, remember, SI units, so 0.01 meters. Cool. So we need to find the current. From here we have the magnetic field strength, which is given to us at 4 times 10 to the power negative 5 Tesla. We have the distance, which is 0.01 meters, because SI units. Cool. So looking at the formula sheet, we can see that there is equation B equals K I over D, and the K is just a constant, which is given to you at 2 times 10 to the power of negative 7. Cool. So we can rearrange for I, which is BD over the constant K. Therefore, plugging the numbers in, 4 times 10 to the power negative 5 Tesla times the distance of 0.01 meters over the constant K gives us a value of 2 amps. And that is the current. Cool. Sweet. Let's explain how the current to the wire CD affects magnetic strength in the region between two wires. So using the same thing, we know that this is north, this is south, because the current flows from north to south. So I can use the same thing. You should probably use the rule you know, which is a right-hand rule. So from here we can figure out that this will be going in, this will be coming out, and so here the direction for current is opposite. So therefore I can figure out it'll be like this. Cool. So so we can say as the current goes up, magnetic field strength B also goes up. So this is because the magnetic field, so for example, say this is the north magnet, this is the south magnet, it flows this way, these are the magnetic field lines. Here in the middle, the two fields combine. Cool. So here is north, so these two will combine here. So we can say that the current goes up, the magnetic field also goes up, the field between the two wires is stronger, and that's because the magnetic fields from the two wires combine, and that's because they're in the same direction. So they're in the same direction as, because they flow from north to south, and south is right here. So they flow intertwined, and therefore it is combined. Okay, next, that's it. Sweet. Once again, if you have any questions, let me know in the comment section. I'll try to reply to all of them. Otherwise, thank you for watching.